Have you ever just stopped and wondered how the vibrant, complex world you see on your screen gets translated into the silent language of a computer? I mean, we're about to peel back all those layers, starting with just a simple, colorful image. But you know, the ideas we're going to uncover, they apply to everything, from the music you stream to the websites you browse. It all comes down to the computer's simple little secret. It's all just ones and zeros.
So that's really the big question, isn't it? How does all this rich visual information, all these colors and shapes, get squashed into a world that only has two states, on or off? It seems kind of impossible, but trust me, it's the foundation of literally everything digital. Okay, so to answer that question, we first need to get a handle on the computer's native language. It's a world built entirely on, you guessed it, just two numbers.
Let's start with the absolute smallest piece of information there is. It's called a bit. The easiest way to think about it is like a tiny, tiny light switch. It can be off, which the computer sees as a 0, or it can be on, which is a 1. That's it. Every single thing a computer does, no matter how complex it looks, just boils down to a massive, massive collection of these simple little switches. Now, a single bit on its own, well, it doesn't tell you a whole lot, right? So to make them useful, computers group them together into little teams of 8. And this group of 8 bits, that's called a byte. A byte is the standard unit we use for, well, pretty much everything, like the size of a file on your computer. So here's where it gets interesting. We live in a decimal world. Everything we do is based on 10 digits, 0 through 9. But computers, they live in a binary world, based on just 2. It's a completely different way of counting and representing, well, everything. But it's this simplicity that makes it so incredibly powerful. Okay, so we've got bits and we've got bytes, but how in the world do you get from a bunch of ones and zeros to actual letters, words, and sentences? To do that, we're going to need a translator. And that translator is called ASCII. You can think of it as a universal dictionary for computers. It gives a unique number to every single character you can type. An uppercase A, a lowercase z, the number 7, even the exclamation point. Yep, they all have their own special number in the ASCII codebook.
So let's see how this works in practice. Take the letter A, for example. In the ASCII system, it's assigned the number 65. The computer then takes that number and just converts it into its binary form, which is 0100001. And just like that, a character we understand becomes a byte of data that a machine can actually read. Pretty cool, huh?
As you can probably imagine, staring at long strings of ones and zeros would be a total nightmare for any human being. So to make life a whole lot easier, programmers came up with a handy shorthand system called hexadecimal. Hexadecimal is what we call a base 16 system. To get 16 symbols, it just uses the numbers 0 through 9, and then it borrows the letters A through F to represent values 10 through 15. Now, the real magic here is that each single hex digit perfectly represents a group of 4 bits. It just makes it a much, much cleaner way for people to read and write binary code.
All right, now we have all the building blocks. We've got bits, bytes, ASCII, and hex. So let's go all the way back to our original mystery and see how all of these concepts come together to create that digital image we started with.
This slide really breaks it down perfectly. What we see as a smooth, continuous image is actually just a giant grid of tiny little squares called pixels. Each one of those pixels is assigned a very specific color, and that color is defined by a set of numbers. And those numbers, of course, are ultimately converted all the way back down into binary for the computer to store.
The most common way to define that color is something called the RGB model. It's actually really clever. It mimics how our own eyes work by mixing different amounts of red, green, and blue light. Each color gets a value from 0, which means none of that color at all the way up to 255, which means full intensity.
So let's look at a really simple example, pure red. In the RGB system, that's maximum red, no green, and no blue, so its value is 25500. Now, in hexadecimal, which you see used all the time in web design, 255 translates to FF, and 0 is just 00. So pure red becomes the code #FF0000.
So this brings us to what might be the most important point of all of this. Context is everything. That binary string we saw earlier, 01000001, doesn't inherently mean anything on its own. If a program is told to interpret it as a number, it's 65. But if it's told to interpret it as text using ASCII, it's the letter A. The raw data is exactly the same. The meaning completely depends on the software that's reading it. Now, you can imagine a single image with millions of pixels, and each one has its own color code. Well, that creates a massive amount of data. So how on earth do we manage all of that without our devices filling up instantly?
And that leads us to one of the most important ideas in all of modern computing: data compression. You could call it the art of saying the exact same thing, just with way fewer bits.
And there are basically two main flavors of it. Lossless compression is like a perfect vacuum seal. It shrinks the file down, but when you open it back up, every single bit is exactly as it was. This is absolutely crucial for things like text or computer programs. Then you have lossy compression. This is the clever one. It permanently throws away tiny bits of data our eyes and ears won't really miss, making files like JPEGs and MP3s much, much smaller.
And believe it or not, there's one more hidden layer to all this: metadata. This is literally data about the data. So it's not the picture itself, but it's information like the date you took it, the camera you used, maybe even the GPS location of where you were standing. It's all the extra stuff that helps us organize and add context to our files.
So as we start to wrap this up, what's the big idea? What's the main takeaway from this whole journey from a colorful pixel all the way down to a simple bit? Well, it all comes down to a really powerful concept called abstraction. Abstraction is the magic that makes all of modern technology work. It's really just about building layers that hide all the messy details below. We don't have to think about the millions of ones and zeros that make up a photo. We just see the photo. Each layer, from bits to numbers, from numbers to text, from text to colors, is just another abstraction, a smart simplification that lets us build these incredible systems from incredibly simple parts. And this kind of leaves us with a final thought to chew on. We've seen how computers take our complex world and translate it into simple data. But that translation, it's always a simplification. So as more and more of our lives are digitized, it's worth asking ourselves what essential details, what nuances of reality might be getting lost in that translation.